So okay, now we're on the desktop, and when we're talking about the lattice light sheet, we usually talk about this in terms of being great for imaging live cells or live embryos. But it's actually really good for tissues as well, particularly with expansion microscopy, and this is an example of that. So this is a data set where the customer had collected this with an inverted microscope, and this was imaging in expansion microscopy, and you can actually see as you go through the Z-stack, now looking at it from right to left, those colors kind of disappear. That's the sample photobleaching. And this is a common problem for expansion microscopy because as you expand your sample, you're expanding in X, Y, and Z. So now if you want to take a Z-stack, you have that much larger of a Z-stack to take. And in addition to that, you're removing a lot of your backscattering. So that's the thing that's going to give you a lot of your fluorescence in the first place. So it's very difficult to get signal, and you have to take a much larger Z-stack. So this one, not surprisingly, was photobleaching as they were trying to go into a 300 micron thick section. They were getting about 9 microns into it. Okay, so I'm going to let this play, and I will drop in, this is a pixelated version because I'm going to show the data set that we collected on the lattice light sheet when we got this sample in our hands. And this will zoom out and out. And so what they were able to do on the inverted microscope was the best Z-stack that they were able to get after trying a number of inverted systems. And now we're looking at this section. You can actually see that we're looking at a brain. And this image that we took, this volume, was a volume that was over 700,000 times larger than the best Z-stack that they were able to get on a confocal or an inverted system of any kind. Right? And so that's really what we're talking about when we're moving to the system. It is not a small change. It is enormous. When we talk to people, we often get the question of, is this going to be faster or is this going to be gentler on my samples? The answer usually isn't that. It's how many orders of magnitude of an increase are you going to get in gentleness or speed? And is it going to be 2 orders of magnitude, 3 orders of magnitude, or in this case, 6 orders of magnitude? It just depends on what your application is, but you can get some truly incredible results. So another one that's a little bit more in line with what we talk about for the system is, let's take a look at this time lapse looking at some cell culture. So this is me experimenting with very, very long time lapses because when we first released this system, we'd always get the question of, well, how long can I image? And I hadn't done that personally. I hadn't tested it. So this is me taking a time lapse that's 7 days long, mixing these 3 cells in a dish. And what I'd like to point out is if you focus on the bright green cells, then you'll notice some unusual behavior. The other 2 cells are very well behaved. Those are becoming contact inhibited, and they more or less stop dividing. The green cells, though, as soon as the plate becomes confluent, they just crawl on top of the other cells, and they continue being incredibly mobile, which in and of itself is incredibly unusual. And so now, as you're watching it, think about the fact that those green cells are actually MDA231s. It's a very aggressive form of breast cancer, very metastatic form of breast cancer. And so I'll back up. Well, actually, now I'll go forward. Now we can actually see them essentially metastasizing. And this was an experiment that we did where we didn't actually even have any question that we were trying to answer, but because we were able to take a video, it was imaging every 5 minutes for an entire week. And this is a 3D, every time you image, you're getting 3D data with the lattice light sheet. Then we were able to just learn so much about each individual cell. And if you watch each individual cell type, you learn a whole lot about those as well. They have their own personality, for lack of a better term. So it's extraordinarily helpful to be able to get more time resolution in your videos, to be gentler, be able to image more often. And this translates also to being able to image very, very rapidly, being able to get 3 volumes per second when you're imaging a cell and getting all the advantages of being gentle, right? So how does this actually work? Let's talk about what the lattice light sheet is and what it's actually doing, right? So I've got some information here that we can go over. Let's take a look at some information here. There we go. That's better. Okay, so looking at the lattice light sheet technology, let me turn this on. There we go. When we're talking about this, the way that I like to present it is we have three different kind of paradigms of imaging. So at the left, we have upright imaging, and this would be examples of wide field, confocal, spinning disks. And it's quite a statement to lump all three of those together, because if you go from wide field to confocal to spinning disk, then it is going to be gentler. But they're all based on the same fundamental principle. And that is that when you're taking Z-stacks, you have to illuminate the entire sample each time. We'll get into that in just a moment. Then the next level up, you have expansion microscopy, or light sheet microscopy, where now you're being very, very gentle on the samples for reasons that we'll mention in a moment, but you're sacrificing resolution. So this is really for imaging tissue samples or entire brains, where you need to go through an enormous volume on the scale of millimeters to centimeters. But you're not going to get that intracellular resolution, that confocal-like resolution. And so that's where we have, on the other side, lattice light sheet microscopy. And so in this case, we're getting the same level of resolution as something like an inverted system, confocal, or better than wide field, but we're getting all of the advantages in terms of speed and gentleness that you would get from a light sheet, right? And so how does that actually work? Well, if we're talking about inverted systems, then you've got two options here with the epi-illumination. Then we have one objective. We're sending the light into the sample, and then we're collecting with that same objective. And so if you want to collect a Z-stack, then you have to focus on, for instance, in this case, the bottom of the sample, and then take an image, and then move your focal plane up, take another image, move the focal plane up, take another image. But of course, this entire time, the sample is being illuminated all the way through it, right? So even though you're focusing on a smaller portion or a single plane of the sample, you're still sending the light all the way through. And so if you have a Z-stack that is going to be 50 sections, then you're illuminating it 50 times every time you take a Z-stack. Right? Light sheet microscopy is a solution to this, because you have an objective that is sending your light sheet through the sample, and then you're collecting it with your collection objective here. And so now you are only illuminating the exact plane that you're imaging every single time. And you can go through the entire sample, and you only illuminate the volume a single time. So we've gone from maybe 2 orders of magnitude for cell culture to 1. Let's actually take a look at that. So this is an example of what I was just saying, taking some multiple images. And if you do the math when you're using a 40x or a 63x and you're looking at typical cell culture, then you're looking at around 50 sections per image, right? And so we're on the order of 2 orders of magnitude fewer images taken with the lattice light sheet in this case. This is a little bit of an example of the lattice light sheet. The difference between the lattice light sheet and a light sheet is that it's using a different type of beam. It's a Bessel beam instead of a Gaussian beam. Not going to get in that too much for today. That's for a deeper conversation. So skip over this a little bit, but you can actually see if you do compare these to a spinning disk, then obviously there's going to be an exponential drop-off with the spinning disk, but you're getting very, very little photo bleaching with time lapses on the lattice light sheet, right? And so lattice light sheet technology is truly incredible and truly gentle. But the reason that we're talking about this instrument today is because the innovation that ZEISS has brought to this is the ability to take this amazing technology and turn it into a turnkey system. And it's not just that it's easy to use. I actually think that it is the easiest light microscope that we have to use. And I want to explain why that is here in just a moment. Right? And so part of this is that ZEISS was able to turn this into an inverted system. So you need orthogonal optics to make a light sheet collection paradigm work. But in this case, it makes it difficult you can't send your beam in from the side if you want to use typical dishes like that 96-volt plate that you see there. But we need to still have those orthogonal optics. So what we have is the light sheet is coming in at a 30-degree angle, and then we're collecting it at a 60-degree angle. And with that, we have a beam that's going through the sample, and we can just scan the sample through that beam. And that's how we're able to accomplish this in an inverted system. And what this means is that you can actually take the samples that you already have, whether it's 96 well plate or a 35 millimeter dish, whatever you're already growing your live samples on, and you can put it on the system and get all the advantages of lattice light sheet imaging. So it's extraordinarily simple. But let's show that in a little bit more detail. So we'll go back to our desktop, and now we'll hop into the software. Right. And so what we're looking at here on the screen is the view of that camera. And so we're looking at a 30-degree cross-section. If we're going from bottom to top here, then you can see in a moment we'll be looking at these cells live. But this is the bottom of the cells and going up through them at a 30-degree angle. We always have people take a few minutes to get used to looking at the 30-degree angle, but I want to show why that's so great. If I go continuous here, then we're looking at a black screen, right? This is what you would see if you just sat down at the system. And if you just sat down at any system. First thing you need to do is find the focal plane, right? Well, on here, one of the many nice things about this new stage that we have on here is that I know that I can just go to this specific number. In this case, it's -600 for this 35 millimeter dish that I have on here. And there we go. There's our sample. So this is collecting a 300 micron range from top to bottom. So remember, since we're sending this sheet through at an angle, we actually have Z that we're collecting every time we scan. And what this means in this case is that there's no longer the concept of a focal plane. You don't have to find the focal plane of whatever you're imaging. In this case, the live cells, also is true for embryos. There's a focal region, and you have 300 microns of distance here. In true Z, that's 300 microns times the sine of 30, which turns out to be half of that. So 150 microns from top to bottom, where now you can use that to find your sample. So very, very easy to find samples. And as you mentioned in that expansion microscopy example, that was really useful because for anybody who's ever imaged expansion microscopy on an inverted system, you know that finding that first Z plane is very, very difficult. It's very difficult to define your focal plane. Okay, so now we've found these samples. I don't need to collect all of this Z, so I'm going to actually crop that down. And I'm just going to say optimal here. Let's hide all the stuff that we don't need. And now if I snap an image, we'll just have our cells there and very little black space on the top and the bottom, right? And move that down just a moment, or just a little bit. And that's it. We're ready to go. If I hit start experiment, then what I've got on here right now is it's going to collect a 50 micron region. So it's going to scan, you can see the animation there, scanning the sample through a distance of 50 microns. And that was 167 images that it just collected. I'll do that again so you can actually watch it. And so from side to side, it's 300 microns. And we just scanned this distance of 50 microns. And so you can see how easy it is to collect enormous volumes with this. Every time you scan, you're getting 3D information. All right, so let's do that again. I'm actually going to expand it out to 100 microns. Hit start experiment, and you can watch this collect the 334 sections that was times the 2 channels that we just collected, right? And so you can see how fast it is when you're able to do things like this. And if we go over to, we always have 2 PCs. This is the processing PC where we're actually storing the data and we can do whatever processing or analysis we want. And so now I can look at this in 3D and you'll be able to see what your cells actually look like. And there we go. So what we're looking at here are some cells that are labeled with H2B in red. That's a histone binding protein. In red, so you're looking at the nuclei. And in green, that's N-binding protein 3, EB3. So in here, you can actually see some microtubules that are arranging here right before this cell divides. And the rest of these, it'll look like little comets shooting through the cells as you take Z-stack time lapses. And what's also unique about this is that you may be able to tell that I'm looking at this from the side and not really using too much caution doing that. If you were to do this with an inverted microscope, because you're illuminating and collecting with that single objective, you actually have an extended point spread function. And the practical application of that, or the practical ramification of that, is that you will get a really smeared z-axis. And so you can't turn your samples on their side. But the lattice light sheet, on top of all the other benefits, has nearly isotropic resolution, or what I typically call functionally isotropic resolution. So you can turn it on the side and actually go in here and you can look at this chromatin and take measurements in X, Y, and Z. And so this is truly 3D data in every sense of the word. You're nearly isotropic voxels, and the entire instrument is designed around the concept of taking 3D or 4D data. So let's go back and actually extend that to 4D. So if we wanted to do a time lapse, then we can just click here, time series, and let's do 20. So I'll do 20 cycles and change that back to 50. Let's get a good time resolution here. If I hit go, start experiment, now we can see this zipping through, collecting 300 microns width by 50 microns long each time. And so if we look at the maximum intensity projection of this, then we can actually watch each time point as it comes through. And so you'll actually be able to see these M-binding protein fluorophores shooting through there in the cells. Isn't that great? I love watching these. And I should point out also that actually M-binding protein has a lot of unbound protein as well. So this background in here is real. That is actual fluorescence. And it just happens that the EB3, when it is on the microtubules, the tips of the microtubules, is much brighter. So we're able to see it very, very well. And so that's collecting our 3D data set, our 4D data set. If we want to, again, look at that in 3D, then we can go over to our processing PC. And once again, we have this in 3D, and I'll let that load up. And now we can watch this. And we can follow each one of those end-binding proteins through these cells. And so this is now a tremendous advantage. If any of you out there are looking at tracking or quantifying the movement of anything inside of a cell, then now you have the time resolution that you would need. You have the gentleness. And actually, I didn't even mention that. I didn't even think about laser power in this case because I just don't have to worry about photo bleaching. It's so much gentler than anything else that exists. Photo bleaching in this case just was not going to be an issue. It's not even a concern. And so a conversation we often have is, what experiment would you design if you didn't have to worry about photo bleaching anymore? What would that look like? Can't guarantee that that is actually going to be literally the case, but it gets closer to the reality of what you can do with this system oftentimes. And so now, if I wanted to actually segment and track all of this, I'm getting such high time resolution that I can follow these through the cell, and because they're isotropic voxels, I can actually get measurements in X, Y, and Z as I'm going through this. So you can imagine, extrapolate this to your own research, whether it's embryos for embryonic development or cell culture like this or anything else, then I hope you can see the potential of being able to image, getting orders of magnitude gentler. And the thicker your samples are, if you're going to embryos, the more advantage you get because you're collecting 150 microns every time you scan. And you can really reach deep into those samples and replace those timely Z-stacks and damaging Z-stacks that you used to have to take on your confocal or your spinning disk, and replace it with a single scan that's very gentle. And on top of being very gentle, it's very fast, and going from hundreds of scans to one means that you can also turn up your laser power. You're getting higher signal to noise, so you're getting better data, isotropic voxels, and you're still able to go faster and be gentler. So I hope that that's a good quick demo of the Lattice light sheet. And with that, I'll mention that we go back to our presentation here. I'm going to skip down and say thank you. If you'd like, you can get on and see the upcoming workshops that we have. I'll try to get out of the way of each one of these. If you'd like to check out our workshops or our upcoming live streams, we'll have one every week. And with that, I'll say thank you, and we'll see you next time.